Second session. The first talk is going to be by François Guillard, and he's going to talk about drag and lift forces in granular flows. François?
So good morning, everyone. I'm François Guillard. I'm a PhD student in Marseille with Olivier Pouliquin and Yann Forfer. And I'm going to talk about the forces experienced by an object in a granular flow. So, first of all, why is it interesting? Sorry. So, why is it interesting to study granular forces? Well, of course, there's a lot of application in industry, for example, in agriculture for plowing. There's also several interesting things in biology, like biological motion for animals, or plant growth and root growth. And from our fundamental point of view, it's also a very classical problem in fluid mechanics. And it's a good way to test rheological properties of fluids, and in particular of complex fluids. So there have been several studies on granular forces. Quite a lot of studies have focused on drag forces, so forces in the direction of the motion. So there, for example, this one by Piper and Barabasi, Kiefer and Albert, where they dragged a vertical cylinder in a granular bed. There's also this one by Brzezinski and Durian, where they rotate a horizontal cylinder. And what is commonly known is that, well, in this case, the drag is proportional to the depth. This can be easily understood because all the forces exerted by the grains are frictional forces, which are proportional to the pressure of the grain. And far from the wall, the pressure is just the weight of the grain above the object. There have been less studies on lift forces. There's mainly this one by Ding, Gravish, and Goldman, where they dragged a horizontal cylinder and they measure a lift force which is proportional to the depth. But in this case, the question is there can be two origins for the lift force: either the free surface that breaks the symmetry, or the pressure gradient, the gravity, that also breaks the symmetry. So which one is in action in this case? So that's why to better understand that, we made this experiment where we have a tank full of glass beads of 500 micrometers. The tank can rotate around its vertical axis, and we put in the middle a horizontal cylinder that is kept static, and we measure at the top the torque experienced by the cylinder when we rotate the granular bed, which gives us directly the drag force on the object. And we also have everything on a weighting scale that directly gives us the lift force on the object. So in all these experiments, we are working at very low speed, so in the quasi-static regime. So all the forces are independent of the velocity. Okay. So now I'm going to focus only on the first half rotation drag. So before the cylinder goes through its own weight, we'll see later why this is important. So what about the drag force? Well, as expected, we see here that the drag is proportional to the depth for various cylinders and of various diameter and length. And what we see is that we can easily rescale the drag by the cross surface of the cylinder, and we have a good collapse of all of our curves. So, as expected, we find a drag which is proportional to the depth in the granular bed, so proportional to the hydrostatic pressure. So that was expected. Now, what about the lift force? Well, first of all, so here I've plotted the lift as a function of the depth. First of all, what we see is that we measure a strong lift force which is about 20 times the buoyancy, the effective buoyancy of the cylinder, and which is pointing upward. But also, the behavior of the lift is completely different from the one for the drag. Whereas the drag increases linearly with depth, we see that the lift at the beginning increases with depth, but then saturates when we are far enough from the free surface. So now, of course, we can do that for different cylinders of different lengths and different diameters. And since the only source of the symmetry of our system is the pressure gradient when you are far enough from the free surface, we expect that the pressure gradient be the relevant scaling for our force. So the lift has to scale as the buoyancy of the object. And so that's what we see here. If we rescale the lift by the buoyancy, we see that we have a good collapse of our curves for various cylinders, as long as the diameter of the cylinder is high enough compared to the grain diameter. If we are less than, let's say, about 10 grain diameters, well, the collapse is not as good. So now we're interested how does this force emerges from the pressure distribution around the cylinder. This is quite hard to have experimentally. So we did molecular dynamic simulation. So it's quite the same configuration. We have just a cylinder. Now we drag the granular bed around the cylinder, so the simulated granular bed. And well, so we can access the pressure distribution around the cylinder. And what is interesting in simulation is that we can do two different things. We can do the classical experiment with a granular bed under gravity, which gives us a mean pressure around the cylinder and a pressure gradient. But we can also just turn off the gravity on the grains in the bulk, so we don't have any mean pressure. But by adding, so we don't have any pressure gradient. But by adding a heavy top layer of grains, we can have the same mean pressure than before, but without the pressure gradient. And so this is the kind of thing we can have. So the grains come from the left, and we see that we have this high pressure bubble that we see yesterday at the front of the cylinder, and the low pressure behind the cylinder. And what we see, I'm not sure if it's very clear, but here, without pressure gradient, the bubble is completely symmetrical. And here, when we turn on the pressure gradient, the bubble is shifted downward. And this is enough to create the lift in conjunction with the fact that we have an high pressure here. And now we can plot the pressure distribution for various depths or equivalent depths here. The dotted lines are without pressure gradient. The plain lines are with pressure gradient. And what we see, it's more clear here, is that by adding the pressure gradient, the pressure distribution is shifted behind the cylinder. And what we see is that even if the pressure increases with depth, actually the difference between the symmetrical and asymmetrical case is independent of the depth. So this is the subtraction of symmetrical case and asymmetrical case, which no longer depends on the depth, which was expected since the lift no longer depends on the depth when we are far enough from the free surface. Okay, so now, as I told you, this was only on the first half rotation of the cylinder in the granular bed. What happens now if we keep rotating? Well, actually a new effect appears on the granular drag. Here, I've plotted the drag as a function of the number of rotations for several depths of the cylinder in the granular bed. So this is experiments now. What we see is that on the first half rotation, as I've shown you before, the drag increases with the depth. That was expected. But after half a rotation, we see that there's a huge drop of the drag force, and which eventually reaches a steady state at long time, and a steady state that seems quite independent of the depth of the cylinder. Perhaps it's more clear here. The red curve is the first half rotation drag, which is linear, as we have seen before. And the steady state drag, close from the free surface, increases with depth, and then saturates at a constant value. So this means that the cylinder no longer feels the weight of the grains above it. It's like there is a structure that is created by the repeated rotation of the cylinder, the fact that it goes through its own wake several times. And this structure screens the hydrostatic pressure of the grains above. But now, what is the scaling for this drag force? Because the previous scaling was with the hydrostatic pressure, but it's no longer a relevant scale for the drag. So we have to find another pressure scale for this force. And what we found is that actually the relevant pressure scale seems to be the one constructed on the length of the cylinder. So as if the cylinder feels a pressure which is rho g times its length. So that's what we see here. We see a good collapse of the steady state drag for several cylinder lengths and diameters. Once again, apart from small size effect, when the cylinder aspect ratio is less than about 10. So here we have a drag which is proportional to the length of the cylinder, and of course always proportional to the surface of the cylinder. The funny thing is that it can allow us to dig without having high torque. So now if we do the experiment, we rotate the granular bed, but at the same time we plunge slowly the cylinder in the tank. So it's like if the cylinder goes through an helix in the granular bed. What we see is that if we go down too fast, the drag increases with depth, as we have seen every time before. But if we if we go down slowly enough, actually, we lose the structure to create and to screen the hydrostatic pressure. And so we can go at a high depth, but we never reaching high torque. And we see that it's really it's quite an important decrease of the torque. It's about a third than what we measure if we go too fast. So to conclude and to sum up, on the first half rotation, the drag is proportional to the hydrostatic pressure, so to the depth in the granular bed. The lift force is independent of the depth if we are far enough from the free surface, but is proportional to the pressure gradient. On the steady state, when we keep rotating, the drag itself becomes independent of the depth and depends only on the length of the cylinder. I haven't talked about the lift force on the steady state. Actually, the scaling are quite the same than in the first half rotation. So to conclude, we have shown that there's a strong lift force that appears when we drag or rotate an object in a granular bed, and which is pointing upward. independent of the depth and which has the same scaling than the buoyancy. Of course, the idea behind that, well, the perspective would be to see if the continuum modeling of granular material are able to predict this kind of force, first qualitatively and then quantitatively. So we are continuum simulation would be interesting. And we have also seen that the fact to go through the fact that the cylinder goes through its own wake create a structure in the granular medium. And of course, it would be interesting to have a better understanding of how the pressure distributes, how the grains distribute. And so this would probably be interesting to do in like molecular dynamics or numerical simulation. Thank you.
Well, I appreciate how quickly you came up with your talk, so we have plenty of time for questions.
Yes, so I think what you're saying that you think there's sort of tunnel that's forming where the pressure is very low, where your object is going, right? And how do you understand why it's not collapsing? It's really low pressure. Since
no, it's not really a tunnel.
it's full of material, but it's at very low pressure. Is it what you have in mind, that there's
No,
a region where
no,
the pressure is low?
Here we are in a quasi-static regime, so actually there's not. We don't think that there is a real change in the volume fraction, for example. What we have in mind is more a redirection of the forces of the grains that are above to the not to the side to the part of the grain that are not moving. And
Do you see this in numeric? Your article?
more or less. We can talk about that. But if I can add just something, is that this effect is robust. If we stop rotating and start again, the effect remains, and so it's not really a weight; it's more a structure.
Okay, Rodrigo, you next.
Yes. In the helical case that you showed, there appear to be some oscillations.
Yeah.
You understand what's going on there?
Yeah, sure. This is probably a small asymmetry in our experiment, small vertical asymmetry. So this is actually the turn. Each turn we see perhaps the preparation was not perfect. So,
Okay, next question, Jim Michael.
So the lift force you're measuring, this is like a large intruder, so you're basically measuring the segregation force on the particle.
yeah, sure. That was also the idea behind to see if this is related at some level with the fact that big particles segregate. We haven't really done that either. We are beginning that right now.
Yeah, just interesting results. They seem kind of similar in terms of general effects to some work that's being done by people looking at pipelines in seabed situations. So you get a situation where pipes can self-bury as a result of cyclic ratcheting of the pipe. So it's kind of like you, rather than the soil shearing past the medium, you've actually got, or were rotating around the medium. It's slightly different geometry, but it seems to be a very similar phenomenon in the sense that you get a burial or an uplift depending on relative weights and buoyancies and so forth. And I'm sort of wondering whether maybe that effect that you get with the continuous rotation is kind of like a reaching, if you're talking in soil mechanics terms, of a sort of a critical state effect, that you're starting off in a, do you see what I mean? Like where you start off
That's
with...
not the answer to that. Let's
Yeah.
go ahead. Otherwise we won't
Sorry.
have time for the next one. You want-
I don't really know.
Once-
In that case, the last question.
Do you see any,
We can talk about
Yeah,
that.
yeah.
do you see any irreversibility or reversibility effect if you go back, for instance, or how much you have to turn not to be reversible when you go back?
Yeah, actually, it's quite it's quite a funny thing because if we reverse in the steady state drag, if we reverse the rotation, the effect, once the structure is created, the effect is the same when we reverse the rotation. So yeah, so actually it's
At some point you cancel it, or if you turn too fast, or if you turn too far.
yeah, of course. If you reach an inertial regime, of course you probably cancel that. We are never in this case. But,
Lily, do you have a short one?
Yeah, just a short question. What do you think will happen if you investigate the influence of the velocity at which you turn? Now you're quasi-static. If you increase it, do you think you will see the effect on the lift?
On the lift, I don't know. I don't think anyone.
And no one has seen that. On the drag, I know that.
On the drag, there has been with
Thank you.
squared.
Yeah.
Great. Thank you very much.